Limits are an important concept in calculus. Limits arise in several mathematical contexts. Here are some examples. 1 divided by 3. 3 goes into 1 0 times. Add a decimal point and a 0. 3 into 10 goes 3 times. 3 times 3 is 9. Remainder 1. Bring down to 0. 3 into 10 goes 3 times. 3 times 3 is 9. Remainder 1. Bring down to 0. And so forth. So you're going to get a bunch of repeating 3's. And so we can say that the limit of 0.333, etc., repeating 3's as the number of repeating 3's goes to infinity is equal to 1/3. So if you stop at any point, you're a little bit less than 1/3, but each time you add another repeating 3, you get closer and closer to 1/3. And so the limit as the number of repeating 3's goes to infinity is 1/3. So that's an example with, I think many of us are familiar. Another example would be that the area of a regular polygon. So a 4-sided polygon would be a square, and then 8-sided polygon is an octagon. But as you increase the number of sides, this is getting to be, it'll get more and more like a circle. And in fact, the area you can compute the area of a regular polygon if you divide it up into triangles, and compute the area of each triangle, and then multiply by the number of sides. But the area, as the number of sides increases, is going to get closer and closer to the area of the circle. I think many of us are familiar with this formula here. Area equals pi r squared, and pi is approximately 3.14. But the area of the 4-sided polygon is 2r squared instead of 3.414 rather, and the 8-sided polygon now is 2.8 r squared, and the radius of each case are the same. They're the same radius. And as the number of sides increases, we're getting closer and closer to 3.14, or approximately pi. So that's another limiting, another example of limits. And the ancient Greeks and other civilizations used polygons to approximate the area of a circle. You can also approximate the circumference of a circle in the same way. So we can say the limit of the area of a inside a polygon as n goes to infinity is pi r squared. And near the end of the semester, we will be using limits to compute areas. And in Calculus 2, you'll see more of that using calculus to compute areas and volumes. Okay, so another example of a limit is the using secant lines to approximate tangent lines. So here's the function is in bold here, and the secant line touches the curve in two spots. But as these 2 points get closer and closer together, if we move these points closer and closer to together, we'll get in the limit we get a line that only touches at one spot, and that's considered to be the slope. The slope of that line is considered to be the slope of the curve at that point. So if we label the original point f comma f of x, so this the y-coordinate here is f of x. I'll do it in red. So this point here, we can label it x comma f of x, and this point up here is going to be x plus h comma f of x plus h. Okay, so so the slope, we're familiar with, you're probably familiar with the slope of y2 minus y1 over x2 minus x1. This is, we can label these if you want: x1, y1, x2, y2. So just to the more familiar notation. And if we take the limit as x2 approaches x1, we get the slope of the tangent line. So this is y2 minus y1, x2 minus x1, and if we take the limit, that gives us the slope of the tangent line. And we can simplify this a little bit. In the denominator, x minus x will cancel, so we'll just have an h on the bottom. And this is called the difference quotient. This f of x plus h minus f of x all over h. You may have seen that in pre-calculus. Sometimes they touch on that in pre-calculus, but we'll be working with this formula quite a bit, and that will give us the slope of each point on the curve. And the slopes are important in applications because slopes represent a rate of change. For example, if you have if we turn this graph upside down, we have send a rocket into the air, and the fuel runs out, and so eventually gravity slows it down, pulls it down. But anyway, the slope and if this curve represents the height of the rocket, the slope would represent the velocity of the rocket at each point in time. Slopes are important in applications. Another example of limit is the asymptotes of functions. This function here, f of x equal 2x over x minus 3, if x is large, 2 times infinity, 2 times a million divided by a million minus 3 is going to be approximately 2. For large values of x and x minus 3 are going to be the ratio is going to get closer and closer to 1. So that means that f of x is getting closer and closer to 2. So we can say that the limit as x goes to infinity of 2x over x minus 3 is equal to 2, and that actually gives us a horizontal asymptote. And so it's the way it shows up on the graph. The function gets closer and closer to the asymptote as x gets large. It also gets closer in the negative direction too, as x gets large in absolute value. And so we have a horizontal asymptote at 2, and we also have a vertical asymptote. As x gets, the function is undefined when x is 3, then you have denominator 0. But if x is a small number that's close to 3, for example, if x is 3.00001, and you subtract 3, you get denominator 0.0001, and dividing by a small number gives you a big number. So as you approach 3 from the right, you'll have a small positive denominator, and that will make it go up. And as you approach 3 from the left, you'll have, if x is 2.9999, you'll have a small negative a negative number that's small in absolute value, and you'll divide by that, you get approach minus infinity. So we can say that the limit as x goes to 3 from the right is positive infinity. The limit as x goes to 3 from the left is negative infinity, and the limit as x goes to infinity of the function is equal to 2. So that's another example of limits. Let's see, another example. We have infinite sequences, and you'll, if you go on to Calculus 2, you'll work with infinite sequences and series. So here we have sequence 1/2, 2/3, 3/4, etc. And the pattern is n over n plus 1. So if so these numbers are getting closer and closer to 1. If you have a million over a million plus 1, that's going to be very close to 1. The ratio is going to be very close to 1. So we can say that the limit as n goes to infinity of n over n plus 1 is equal to 1. Okay, so we get into some definitions of limits. We're mostly going to take a somewhat intuitive approach, so we're not going to emphasize these definitions too much. But there is, just so you're aware, there are precise definitions of limits, the limit as x goes to a of f of x is equal to L if f is defined in an open interval containing a except possibly at a itself, and if for each epsilon greater than 0 there's a delta greater than 0 such that absolute value of f of x minus L is less than epsilon if x minus a is less than delta. So intuitively it says that if x gets close to a, then f of x is going to get close to L. We could that's a two-sided limit. We could also define a one-sided limit, limit as x goes to a from the left of f of x is equal to L if for each epsilon greater than 0 there's a delta greater than 0 such that absolute value of f of x minus L is less than epsilon if a minus delta, if x is between a minus delta and a. So this says that if x gets close to a from the left, then f of x gets close to L. So that's a limit from the left. And the limit from the right would be analogous to that. If the limit as x goes to a from the right of f of x equal L, if for each epsilon greater than 0 there is delta greater than 0 such that absolute value of f of x minus L is less than epsilon if x is between a and a plus delta. So this says that x is going to a, approaching a from the right. So it's a little bit more than a, but it's getting closer and closer to a. And when that happens, f of x gets close to L. We could also so that L is would be a finite number. We could also define infinite limits. Limit as x goes to a of f of x equal infinity if for each m greater than 0 there's delta greater than 0 such that f of x is bigger than m if absolute value of x minus a is between 0 and delta. So that says if x gets close to a from either direction, then f of x gets large. So this is infinite limit. We can also take make a definition for as x goes to infinity. So this is as x goes to a, f of x goes to infinity, but we can also make a definition for a limit as x goes to infinity. The limit as x goes to infinity is equal to L if f is defined on a to infinity, and if for each epsilon greater than 0 there's n such that f of x minus L is less than epsilon if x is greater than capital N. So intuitively f of x gets close to L as x gets large. And similarly, we can define the limit where x and f of x both go to infinity, and one side limits as f at infinity. I mean, when f of x goes to infinity, and so forth. So we can have some other definitions, but we're not going to sort of emphasize these epsilon delta definitions. We'll take a somewhat more intuitive approach, but these definitions are used to prove theorems, there's some of the theorems will be useful. The limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. Limit of a constant times a function is the constant times the limit. Limit of a product is the product of the limits. A limit of a quotient is the quotient of limits as long as the limit of the denominator is not equal to 0. The limit of you can take the limit inside an exponent. Limit of f of x to the n power is equal to the limit of f of x, and then taken to the n power. Limit of a constant is that constant. Limit of x as x goes to a is equal to a. The limit of x to the n as x goes to a is a to the n. The nth root, limit of the nth root of x as x goes to a is the nth root of a if n is odd or a is greater than 0. Limit of the nth root of f of x as x goes to a is the nth root of the limit of f of x as x goes to a if n is odd or limit is greater than 0. The limit as x goes to a of f of x is less than or equal to the limit as x goes to a of g of x if f of x is less than or equal to g of x at near a, except possibly at a. So a lot of these are sort of intuitively what you would think they would be, but to prove them precisely you need to use the precise definition of limit. Limit as x goes to infinity of x 1 over x to r is equal to 0 if for r is greater than 0. Limit as x goes to minus infinity 1 over r x to the r is 0 if r is greater than 0 and if x to the r exists. There's a useful theorem called the squeeze theorem or the pinching theorem, it's a limit as x goes to infinity of g of x okay, the limit as x goes to infinity of g of x. So g of x is between f of x and h of x, and if the two functions on the end, if f of x and h of x both have limits of L, then the pinching theorem or the squeeze theorem says that g of x itself will have that same limit. And another useful theorem is that if f of x is continuous and you have a composite function, the limit of f of g of x is the same as the f of the limit of g of x. So you can take the limit inside the component as long as f of x is continuous at the limit as x goes to a of g of x. That's also a very useful theorem. And then a couple of limits that will be used in when we compute the slope. Will be useful when we compute the slope is limit as theta goes to 0 of sine theta over theta is equal to 1. You could from the graph if you remember the graph of the sine function, it looks something like this. And the graph of this is sine of x. Okay, maybe I probably should have done the coordinate system in black, function in blue, but okay, so that's the graph of sine x, and then if we did the graph of x, from the this is f of x equal g of x equal x. This is sine x, and you see the From the graph, it looks like the ratio between them should be pretty close to 1. The proof is a little bit more involved in that, but anyway, the limit as theta goes to 0, sine theta over theta is equal to 1, and also the limit as theta goes to 0, 1 minus the cosine of theta over theta is equal to 0. So those are useful in computing the slope of these curves, and we'll get into more. You'll see that a little bit later. I think next week or the week after. Okay, so let's do some limits here. Now, if we plug in 1 here, we're going to get 0 over 0. For continuous functions, the limit as x goes to 1 is just going to be f of 1, or the limit as x goes to a is just going to be f of a. But this function has denominator 0. If we put in a 1 here, we're going to get denominator 0, and we'll also get numerator 0. So if you just plug in the 1, we get it's 1 cubed minus 1 over 1 minus 1, which is going to be 0 over 0. This is indeterminate. But what we can do here is factor this or divide. We could, if we want, we can divide. Let's divide it. We'll do a long division here. So if we divide x cubed divided by x is x squared, so we'll have an x squared on top. Multiply, we get x cubed minus x squared, and then the next step would be subtracting. But the way you subtract algebraic expressions, you change the sign, add or subtract like terms according to the sign. So we'll get a remainder x squared, and we can bring down the 0x, and divide again. X squared divided by x is x, and then multiply, we get x squared minus 1x. Draw the line, change the signs. I'll have x minus 1. Divide again. X divided by x is 1. 1 times x minus 1 is x minus 1. Draw the line, change the signs, and you get remainder 0. So now, if we divide, we can now take the limit again. Try again to take the limit, and now we'll get 1 squared plus 1 plus 1, which is equal to 3. So, if we just plug in the way it was written originally, we get 0 over 0, which is indeterminate. But if we divide, you can also factor and cancel, is another way of doing it. But if we divide, we'll get the quotient is x squared plus x plus 1 with remainder 0. So, so then we can plug in 1 squared plus 1 plus 1 is 3. Limit as x goes to 2. Well, this is continuous at 2, so we can just plug in the number here. 2 to the third minus 1 over 2 minus 1. That's 8 minus 1 over 1. It's going to be 7. So that, for that function, that's continuous at that point there. So we can just plug in the number. Okay. Limit as x goes to 1 from the right. So if x goes to 1 from the right, the denominator will get, it's going to approach 0, but it's going to approach from the positive side, so it's going to be, I'll put a 0 plus here, because it's going to be, as x is close to 1 but not equal to 1, the denominator is going to be a positive. In the numerator, we're going to have 1 cubed plus 1. So we're going to have, that's equal to 2. And 2 divided by, I'm not showing my, so we have 2 divided by something very small. As x approaches 1, it's going to, x minus 1 is going to get closer and closer to 0, but it'll be approach it from this positive side. So this 2 divided by something small is going to be big. So this is going to go to, this limit here is going to be infinity. And then the same problem, if we approach 1 from the left, that means that x will be a little bit less than 1, and we're going to have a small negative number, a small in absolute value. It would be a negative number, and 1 cubed plus 1. So this is 2 over something close to 0 but negative, and so the limit here will be negative infinity. And so so the two-sided limit does not exist. So if you have the limit as x goes to 1, that's the two-sided limit. It does not exist because the one-sided limits don't agree. So we can write DNE, that's a shorthand for does not exist. It's a pretty standard abbreviation for does not exist. Okay, so now we have a function as x goes to infinity of x cubed minus 1 over x minus 1. We looked at that function before at taking the limit as x goes to 1, but now we're taking the limit as x goes to infinity. So this is going to be infinity over infinity, which is indeterminate, because x cubed is infinity. Infinity cubed is infinity, and infinity minus 1 is infinity, so this is indeterminate again. And we already did the long division here. This is the same function we had before. When we did the long division, we got x squared plus x plus 1. So we can write this as the limit x goes to infinity, x squared plus x plus 1. And now infinity plus infinity is going to be infinity. Infinity divided by infinity, we don't know. It's indeterminate. It could be anything. But infinity plus infinity is going to be infinity. So that limit is infinity. As x goes to minus infinity, again, this is going to be minus infinity over minus infinity, which is indeterminate. But we could take the limit x goes to minus infinity of x squared plus x plus 1. Here we're going to get infinity minus infinity, which is also indeterminate. We could factor this limit x goes to minus infinity. Thing is, this is infinity minus infinity, but this term is always going to be bigger than the other one. But let's factor this out. This is x times the quantity x plus 1 plus 1. And now we're going to have minus infinity times minus infinity plus 1. So negative times negative is positive. So this is going to be infinity plus 1, which is infinity. Okay. But generally, if the higher power of x is going to dominate, so that's generally going to be the case. The higher power of x is the dominant one. Okay, the limit as x goes to 1 of x squared plus x minus 2 over x squared plus 2x minus 3. So if we plug in a 1 here, if it's continuous, we can just plug in the number 1 squared plus 1 minus 2 over 1 squared plus 2 minus 3. And this is going to be 0 over 0, which is indeterminate. Okay, so that's a clue that x minus 1 is a factor. If you plug in, if 1 is a root of both the top and the bottom, that means x minus 1 has to be a factor. So let's factor this. Okay, so x times x is x squared. We need two numbers to multiply to negative 2, add up to 1, and we know that one of them is going to be negative 1. Negative 1 times 2. And you can check with the FOIL method. X times x is x squared. Outer product is 2x. Inner product is negative 1x. You subtract, you get 1x. Last times last is negative 2. The other one, we need two numbers to multiply to negative 3, add up to 2. We know that negative 1 is going to be one of them. The other one has to be 3. So now we can cancel the x minus 1s on top and bottom. We can cancel those out, and now evaluate the limit. It's going to be 1 plus 2 over 1 plus 3, which is 3 over 4. Okay. Limit as x goes to infinity. So if we just plug in the numbers, we get infinity over infinity, which is indeterminate. So let's divide x squared plus 2x minus 3 divided into x squared plus x minus 2. X squared divided by x squared is 1. And if you multiply, you get x squared minus 2x minus 3. Draw the line, change the signs. So you'll get a remainder of, this would have been a plus 2x, so this becomes a minus when you change the sign. So minus x plus 1. X squared plus 2x minus 3. Okay, so if we take the limit, this piece is going to go to 1, and then we have this other piece here, but because the degree of the denominator is more than the degree of the numerator, this piece goes to 0. This piece here is going to be dominated by the x squared on the bottom, so that goes to 0, and this piece goes to 1. So the limit is going to be 1 plus 0. It's going to be 1 plus 0, which is 1. Yeah, actually there's a more, just a better way of doing this, that we could generally you just divide the highest power of x by the highest power of x. That's going to give you the limit, but let's do this a little bit more carefully here. If we multiply top and bottom by x squared, or 1 over x squared, that's probably a better way of doing it. We distribute the x squared, and we're going to get 1 plus 1 over x minus 2 over x squared over 1 plus 2 over x minus 3 over x squared. So we take the limit, 1 over x goes to 0. As x goes to infinity, 1 over x goes to 0. So this is going to be 1 plus 0 minus 0 over 1 plus 0 minus 0. And that's equal to 1. Okay, so that's a better way of doing it. Okay, next example. Limit as x goes to infinity of 4x squared minus 3 over 7x minus 2. So this is equal to infinity over infinity. As x goes to infinity, we'll have infinity minus 3, which is infinity, and the top 7 times infinity minus 2 is also infinity. So it's equal to infinity over infinity, which is indeterminate. So let's multiply top and bottom by 1 over x. We want to multiply top and bottom by 1 over x. And in the top, as x goes to infinity, x is going to be positive. So x is going to be the same as square root of x squared for positive numbers. So I can write that this is 1 over the square root of x squared. And I'll take that inside the other square root. So if we distribute, we get the limit x goes to infinity of square root of 4 minus 3 over x squared. I'm distributing the 1 over x squared here, and I distribute the 1 over x here. We get 7 minus 2 over x. And then if we take the limit, we're going to get square root of 4 minus 0 over 7 minus 0. So that's going to be 2 over 7. Okay. Next example. Limit as x goes to infinity of 2x minus the square root of 4x squared minus 3x. Okay, so this is going to be infinity minus infinity, which is indeterminate. So we have to do something with this. And what I'm going to do is multiply top and bottom by the conjugate. So this, I'll write this as 2x minus square root 4x squared minus 3x. And this whole thing times 2x plus square root 4x squared minus 3x, and all over 2x plus square root 4x squared minus 3x. Okay, so I'm just multiplying top and bottom by the conjugate of the original expression. An expression involving a square root, the conjugate is just the opposite. Take the opposite square root. So this is the negative square root. The conjugate would be the positive square root. Okay, so this is so we can simplify the numerator. If we apply the FOIL method here, the outer product and the inner product are the same except for the sign. So the outer product and the inner product are going to cancel. So we're just going to have first times first and last times last. So we'll have 2x times 2x is 4x squared. And then last times last is negative times a negative, negative times a positive. And you'll have the square root times the square root. So you'll just negative times positive is negative, and the square root and the square will cancel, so you have minus 4x squared plus 3x. Let's see, okay. Yeah, okay. It looked like it might have been frozen for a minute there. And this is over 2x plus square root 4x squared minus 3x. Okay, so 4x squared minus 4x squared cancels. So we're going to have this is going to be infinity over infinity. Now, infinity over infinity. It's still indeterminate. Okay, so I'll just rewrite this down here. We started with infinity minus infinity. Now we have infinity divided by infinity. It's still indeterminate. Okay, so let's multiply top and bottom by 1 over x. And we'll distribute the 1 over x. We'll get 3 on the top. 2x times 1 over x is 2. Here we can, when you bring it inside the square root, it becomes an x squared. So we'll have 4 minus 3 over x underneath the square root. And now we can take the limit, and we get 3 over 2 plus square root of 4 minus 0. 3 over x goes to 0. So this is going to be 3/4. 3 over, well, we can write 3 over 2 plus 2, which is equal to 3/4. Okay. So the limit is 3/4. Okay. Okay, the next one. Limit as x goes to infinity, e to the minus x cosine of x. The cosine is always between 1 and -1. So this this one is cosine of x is always between -1 and 1. And if you multiply by e to the minus x, e to the minus x is positive, so we can multiply by e to the minus x. That means that minus e to the minus x less than or equal to e to the minus x cosine x less than or equal to e to the minus x. And now if we take the limit, this goes to 0. E to the minus x is let's write this as minus 1 over e to the x less than or equal to e to the minus x cosine x 1 over e to the x. E to the x is approximately 2.7. It's a positive number. If you raise it to an exponent, it's going to get big, but this is 1 over it, so it's going to be small. So these both go to 0. That goes to 0. This one goes to 0. And by the pinching theorem, this part in the middle also has to go to 0. So the limit there is 0. And by the pinching theorem, or the squeeze theorem, it's in between two expressions that go to 0. Okay, the cosine squared x over x squared as x goes to 0. The cosine goes to 1. The denominator goes to 0. So the denominator is always positive. So this is as cosine. This is going to go to cosine of 0 is 1. So this goes to 1 squared over x squared is going to be positive, whether it approaches from the right or the left. X squared will be positive, so this is equal to infinity. Okay, so sine squared x over x as x goes to 0. So we can write this as limit x goes to 0 of sine x times sine x over x. And the limit of product is the product of the limits. Limit as x goes to 0 sine x times limit x goes to 0 sine x over x. And yeah, one of the theorems said that this goes to 1. Limit is sine x goes to 0, and this piece goes to 1. So it's 0 times 1 is 0. Okay, that was one of the theorems, that sine x over x goes to 1 as x goes to 0. This one, we could write this as limit x goes to 0 of sine 6x over 6x times 3 halves. 9 we can write as 6 times 3 halves. You can flip the fraction, change it to multiplication. Divided by a fraction is the same as multiplying by this reciprocal. So this is 2/3 times sine 6x over 6x. The 2/3 constant can come outside the limit. So we have 2/3 limit x goes to 0 of sine x over 6x over 6x. Now as x goes to 0, 6x will also go to 0. So this is the limit as 6x goes to 0, sine 6x over 6x. So this is one of the theorems. It's of the form let u equals 6x, it's or theta equals 6x. The limit if theta goes to 0, sine theta over theta. And that was one of our theorems. That's equal to 1. So this is going to be 2/3 times 1, which is 2/3. And that concludes this presentation.